Nothing more of it. And then you have the group gamma, which is a group of reflections. So that's generated by these 4 circles. And now what I want to take is the group generated by all the reflections. So I want to reflect not just through these 4, but also through this one and that one and that one and all of them. And it turns out it's enough to reflect just through 4 more, which are the dual 4. Is the picture clear? Okay. Yes, so that's the whole point of having a geometrically finite group, is that being geometrically finite and thin means you have flares. And those flares, because the limit set is the exterior of some spheres, you have these regions at infinity that are cut off by spheres, and there's a finite number of them. So there will always be only a finite number of circles from the packing that I need to take to generate this thing. So will be a finitely generated group, and moreover, it'll be a lattice. Since now we've cut off all the boundary at infinity, all that's left is cusps. Okay, so this will certainly be a lattice, and that's this group, the supergroup. Okay, so supergroup is okay? Once we have the supergroup, what I want to define is the superpacking, which will not be a packing, but what I mean by that is you take the supergroup and you act on the packing itself. So what does that look like in the Apollonian case? Well, this is the superpacking. In other words, you start with the Apollonian group itself, but now you're allowed to reflect through this circle also. So these circles go here, and these circles go here, and there, and so on. So you get this infinite collection. It's no longer a packing. It's now dense because it's a Bianchi group acting in the plane, acting on the boundary at infinity. Okay? Is that clear? Is the notion of superpacking clear? It's infinitely many packings all superimposed. I guess it's I put too many circles in. Now you can't see anything. So maybe in this case the hand picture is better than the computer. But yeah, I was hoping for a big. Okay. I guess someone's taking notes, or maybe they'll post this on. Maybe I'll post these notes online. You can zoom in as much as you want and see that the picture really does look like this. Okay. So superpacking is okay. Supergroup acts on the packing to give the superpacking. So, what does it mean to be superintegral? A gamma packing P is called superintegral if every sphere in the superpacking has integer bend. So it's not enough to have integer bends in the packing itself. You must have, for superintegrality, you must have integer bends in the entire superpacking. So far, so good? And it turns out that the Apollonian group is indeed superintegral. The Apollonian packing is superintegral. Okay, why do I want that? Because now I can state the superpack, I guess it was the election. So this is, I should have said, joint work with Kei Nakamura. So our conjecture is the superintegral packing arithmeticity conjecture, which has the following. If you have a gamma packing P and it's superintegral, then the supergroup, which is a lattice, is actually arithmetic. Okay? That's the main conjecture that I want to highlight and discuss what we can say towards this. Any questions on the statement? So in the Apollonian case, the supergroup was this fundamental domain, with octahedral with all dihedral angles pi over 2, and it was commensurate with SL2Z, so it was indeed arithmetic. SL2Z, Z joint I. Okay. Oh, I was missing a word. That's why you're confused. Is arithmetic. Okay. So this supergroup gamma, which is a lattice generated by reflections, is arithmetic. Okay. So let me immediately remark that superintegrality is necessary. So we have examples of integer gamma packings which are not arithmetic, and I hope to show you that at the end. For which so integer gamma packings, not superintegral obviously, otherwise we wouldn't be making the conjecture, for which the supergroup is not arithmetic. And this is somehow related to examples of Deligne-Mostow non-arithmetic groups. I'll say that later. Okay, so why do I care about superpack? Well, if we could prove this conjecture, it would be extremely useful. For the following reason, there are only finitely many maximal hyperbolic arithmetic reflection groups. So this is a work of many people, starting, of course, with groundbreaking work of Windberg, and then Nikulin, and many others. So there's a finite list. So if you think this Apollonian packing was this kind of magical object, yes, it is magical, because it only happens finitely many more times. That's what this conjecture would say. And in fact, we know that there's a finite number in each dimension, and there's a bound on the dimension where these arise at all. Okay, so it turns out, although initially it was stated as a general problem, it turns out it's a finite dimensional topology problem. Okay? Low dimensional if 30 is low for you. Okay, so superpack would tell you that there are essentially only finitely many superintegral gamma packings. And the theorem that we can prove so far is that this superpack holds for gamma packings, I have to explain what this means, modeled on uniform polyhedra. So let me explain what that is. So any questions before it? The last statement I have to explain, but otherwise, is everything clear? Okay. So what is a polyhedral packing? So let me remind you of this fundamental theorem of Koby-Andreev-Thurston, which in this formulation was claimed by many people, but the only place where it was actually written down, or the first place that I saw it written down was Schramm. So it says the following: every convex polyhedron, so topological polyhedron, admits a combinatorially equivalent geometrization which has a midsphere. So what does it mean to have a midsphere? A midsphere, it means a sphere which is tangent to all the edges. So let me show you an example. So if you don't remember what a cube octahedron is, so this is an Archimedean solid. You start with a cube, and then you start cutting off the corners. And when you cut off the corners, when you get to this, what is that, an octagon? When you get a regular octagon at the faces, that's called a truncated cube. And you keep truncating a little further until the corners actually meet, and now you get squares again, and that's called a cube octahedron, because so you started with a cube and you did this operation, but if you start with an octahedron, which is dual to the cube, and you start cutting the corners until you get to the middle, you get the same shape. So that's called a cube octahedron. So topologically, what I mean is, how many vertices do we have? We have 4 on top, 4 in the middle, and 4 on bottom, so we have 12 vertices. And every vertex has valence 4, there are 4 edges coming out. And around every vertex, there's a square, then a triangle, then a square, then a triangle. So that's what makes it an Archimedean solid. Its faces are regular polygons, and it's vertex transitive. Every vertex looks the same. So that's the combinatorial or topological information you are given, and what the Koby-Andreev-Thurston theorem produces is a particular configuration of the vertices in space such that there's a sphere which is tangent to every single edge. Okay, so I hope you can see this sphere that blows up, and you pull the vertices around in exactly the right way, and this is conformally rigid. There's a unique way of the Mobius transformations of doing this. Okay, they were using this for things like approximations to the conformal mapping theorem. You know, it's a beautiful story that I don't have time to get into, but I want to use this for a different purpose. So what I would like to do is to use Koby-Andreev-Thurston to attach a gamma packing to your favorite polyhedron. You give me a topological polyhedron, I'll hand you back a circle packing. So these are all these circle packings. I probably won't say much about our higher dimensional examples because it's hard to draw pictures of 4-sphere packings. So how do you do this? So once your topological polyhedron is geometrized, the midsphere is also the midsphere of the dual polyhedron. So the dual of the cube octahedron, so let me show it to you. You ready? Watch this. There it is. So that's called a rhombic dodecahedron. So every face is a rhombus, and there were 12 vertices of the cube octahedron, so now there will be 12 faces of the dual polyhedron. Okay, so that's a dodecahedron. So it's a rhombic dodecahedron. And you can see that the midsphere perfectly chops up these two figures, one sitting on top of each other. Okay, so what do you do now? So you get 2 sets of clusters of circles. So this is a circle which corresponds to that vertex, while this is a dual circle corresponding to this space. So you get circles and dual circles on top of each other, which give you 2 clusters of circles whose tangency graphs are topologically the same as the original polyhedron and its dual. So let me show you that in this picture here. So the blue circles, every circle corresponds to a vertex, right? Tangency means the two circles are touching. So the circles are vertices, and an edge between them means they're tangent. So here's a circle. So what you should really see is around this circle, what kind of faces do we have? So here's a square face. I hope you can see 4 sides. And there's 3 sides, and there's 4 sides, and here there's a triangle, 3 sides. So around that vertex is triangle, square, just like the cube octahedron. Okay? So the graph, just the tangency graph of the blue cluster is isomorphic to the original cube octahedron, and I'll let you verify that the tangency graph of the, whatever color that is, red or purple or something, is the tangency graph of the rhombic dodecahedron. So is it clear how I'm getting these two clusters sitting on top of each other from Kobe-Andreev-Thurston? Cluster is just a finite collection of circles. Okay. So finite collection of circles, and what I want is the tangency graph of that finite collection of circles to be isomorphic to the polyhedron that you asked for. Okay? So once you have this, what do? You do the obvious thing. You take reflections through the dual cluster, and you let that act on the original cluster, and that will give you a packing modeled, what we'll say is it's modeled on the given polyhedron. Okay? So let's do this cube octahedral example. There's the cube octahedron again. So what you're given is this combinatorics, or the topology, which is the list of vertices and list of edges from which you could construct a list of faces if you really want to. All we need is the one skeleton. So then you geometrize. Here's Kobe-Andreev-Thurston. That gives you a cluster. Again, around the circle labeled 17 is a triangle, then a square, then a triangle, then a square. So that's the cube octahedral configuration. That's the same for any circle. And then when you let the dual group act, you get the packing modeled on the cube octahedron. Okay? Is this clear? So the graph, what does it mean to be a combinatorial polyhedron? It means to be a 3-connected planar graph. That's an equivalent statement. So these are all planar graphs. And in higher dimensions, we'll need simplices of 1 dimension higher. If that makes sense. It's similar to what's going on here, this extension. Okay. So is it clear how we let the dynamics of the dual group act and we get this gamma packing modeled on the cube octahedron? And as you can see, this one's integral. So the cube octahedron is integral. And we'll call a polyhedron, we'll extend the definition of superintegrality to the polyhedron, or integrality. So a polyhedron is superintegral or integral if there exists some packing modeled on it, which is integral or superintegral. Does that make sense? So lemma, the cube octahedron, not only is it integral, as you can see here, it's actually superintegral. When you take the super packing, you will also get only integer curvatures, only integer bends. Okay, so the real problem is classify superintegral gamma packings, and a subclass of them is classify superintegral polyhedra. Which polyhedra are superintegral? And again, the conjecture is there's essentially finitely many. So let me explain why this is not so easy. So first of all, if I give you an arbitrary polyhedron, I give you a 3-connected planar graph. 3 connected means you can remove 2 edges and it'll still be connected. Okay, so that's the same thing as just draw me any polyhedron you like. I take my kids' magnetiles and just randomly stick them together. I get some polyhedron. Is it integral? Is it superintegral? Well, how do you do this? First of all, Kobe-Andreev-Thurston is an existence proof. It's not doesn't tell you what the answer is. It says there exists some way of pulling these things. So the actual geometrization process is achieved. There are beautiful algorithms by Stevenson and others that let you do the geometrization, but it's an infinite limiting process. So how are we ever going to know if 2.9999999 is actually 3? Well, there's a savior. The Mostow rigidity comes to the rescue, and the fact that we are actually getting lattices in hyperbolic 3 space tells us we have rigidity. And rigidity means you can make all the bends and the centers algebraic. So when you see 2.99999, what you do is you guess that it's 3. Once you see enough decimal places, you guess what the algebraic value is. Then you go back to the tangency and see, do those algebraic values actually give me the tangencies I require on the nose? Okay? So in practice, this is a finite process which then tells you whether or not a given guy is integral, superintegral. Okay, so it's not trivial, but it's not so hard. But even then, there are difficulties with the classification. So here's a theorem of ours. Infinitely many polyhedra are integral and superintegral. Well, that's an immediate corollary, the fact that infinitely many distinct polyhedra actually give rise to exactly the same circle packing. So there's a symmetry group, there's not the symmetry group. Of course, any normal subgroup of your hyperbolic reflection group has the same limit set. So there are lots of ways of realizing the same packing with a different gamma. And moreover, there are genuinely non-isomorphic integral circle packings, and infinitely many of them, all of whom are superintegral. Okay? So if this seems like it's contradicting what the consequence of superpack is supposed to be, which is the finiteness, it's actually not contradicting it, because this theorem is proved by certain gluing constructions along vertices and faces, which I'll talk about a little bit later. These are non-maximal reflection groups. So they're families, so we can produce infinite families from a given superintegral packet. Okay, so there is this infinitude, which makes it hard if you hand me if my kid just puts some triangles and squares together and says, here, Daddy, you know, to do something with this. I have to figure out if it lives in one of these families. But up to maximality, we do believe that there's a finiteness. That's what superpack would predict. Okay, does that make sense? So these are non-maximal reflection groups that are generating these infinitely many non-isomorphic superintegral circle packings. Any questions? Okay, so let's talk about the main theorem again. So what does it mean for a polyhedron to be uniform? As we said, its faces are all regular polygons, and it's vertex transitive. Every vertex looks the same. And so there's an old classification, essentially due to Archimedes, but he's for some reason threw out the prisms and antiprisms, because there are infinitely many of them. So Kepler put them back in. So the uniform polyhedra are the Platonic, Archimedean solids, and prisms and antiprisms. And the reason we wanted to look here first is if you're going to see arithmeticity, these things have Hecke operators. They're very highly symmetric. So these are kind of the most symmetric objects we could think to try. And here's the classification. So as I said, the main theorem is that superpack holds 4 gamma packings modeled on uniform polyhedra, and also their growths. So all of these constructions of infinitely many superintegral circle packings, all of them have arithmetic supergroups. And here's the complete classification. So among the Platonic solids, the superintegral ones are the tetrahedron. What's a tetrahedron? The classical Apollonian packing is the tetrahedron, because it's four circles, all of them tangent to each other. So the tangency graph is the same as the tangency graph of a tetrahedron, right? Complete graph on 4 vertices. Okay? The octahedron is what we discussed, the Skutler, Mallows, Zhang, and Boyd. The cube appeared in work of Stange. If you look at the dodecahedron and icosahedron, they're not integral, and hence not superintegral, but they are what we call golden, so you can make all of the bends integers in the golden mean. Among the Archimedean solids, the cube octahedron that we discussed is superintegral. The truncated tetrahedron, also the truncated octahedron, you can sort of imagine what those guys look like. Then there are a couple more, the icosadodecahedron, which is similar to a cube octahedron. Then you have the rhomba icosadodecahedron and its cousin, great and small. And if you don't know the zoology, never mind. But a bunch of them are golden. Then you have a truncated cube, and rhomba cube octahedra are silver. So silver means that they're, I learned this from Wikipedia, the silver mean apparently is all 2s instead of all 1s in the continued fraction. So these guys are not quite as good as gold. Silver, but when you go to, for example, the snub cube, so you know what a snub cube is? You take a cube, I should have brought my magnetized. You take a cube, and you pull it apart. So that would give you like a rhombic cube octahedron. But then you snub it, you break it, and you snub it. Snub means crooked nose, right? So you take a cube and you pull its sides apart. And what you would have here is rectangles, but then you twist the rectangles, so what you get is triangles. So anyway, around each vertex is like 4 triangles in a square. So that's I think that's right. So that's a snub cube. It has cubic bends, not integers. And the snub dodecahedron has sextic bends. So I don't know when I said Mossad rigidity tells us these are going to be algebraic. I don't know the degree. And presumably the degrees are unbounded. I don't know if they're bounded or not. But the interesting thing is we're no longer, for these much less symmetric guys, we're no longer getting even integers, algebraic integers as bends. And among the prisms and the antiprisms, this is where it gets interesting. The 3 prism, the 4 prism, and the 3 antiprism are all, so you know what a prism is? So a prism is you have an n-gon on top and an n-gon on bottom, and you just drop squares in between, right? That's a prism. So what's a 4 prism? Cube, right? So that's cheating, that's why it's in green. What's an antiprism? You take an n-gon and you twist it by half a rotation, and then you connect by like Homer Simpson hair triangles, like a drum or something. So what's a 3 antiprism? Take 2 triangles, snub it a little bit, and connect triangles. Octahedron. Okay, so those are not new. So the 4 prism and the 3 antiprism are not new. Let's talk about the 3 prism. The 3 prism is also not new. Because the 3 prism is the gluing along a vertex. So what's a 3 prism? Let me draw the 3 prism. There's a 3 prism. This will be the same as if I take a tetrahedron and I double it across the vertex, and then I remove the vertices, and so I'm gluing along a vertex. This is the operation of gluing along a vertex. So what does that mean on the level of circle packings? So if I start with my Apollonian circle packing, one of the vertices, let's say this vertex is the one that I'm going to remove. So I invert through it, and then I remove it. So that's the doubling along a vertex. So it's not new because its superpacking is a subpacking of the Apollonian superpacking. That's what makes it superintegral. It lives inside something else that's non-maximal. That's the non-maximality of this 3 prism. Does that make sense? Is that clear? The 6 prism is very interesting, and I'm going to talk about it later. This is in whatever color this is, light green or something. It's integral, it's not superintegral, and its supergroup is not arithmetic. So this is my Deligne-Mostow example. So I'll come back to this one. And a theorem with a little t, because the details are still written up. For all of these superpackings, you get the same theorem as what I had with Bergan about the almost. So the bends up to x you find relative to the ones you should find tends to 1. And I think Elena is speaking about parts of this on Friday, so you'll get to hear. Sorry, this is not an analytic number theory talk. The analytic number theory is hidden in probably this one. So there's a circle method there, there's expanders, you'll like it. Go to Elena's talk. But that's not what I'm going to tell you about. So let me spend a little bit of time saying how we get all this stuff. Where's this coming from? So what tools are we using? The basic tool is to, and I learned this from Jeff, is to use inversive coordinates. So in some form, these go back to what, Clifford, Darboux? These are kind of the guys I found. So if you have a sphere in space, and it has center z, some point in space, and radius r, what's the co-radius? The co-radius is the radius of the sphere you get by inverting through the unit sphere. So I'll take this sphere, I invert through the unit sphere, I get some other radius. That's this co-radius. Exercise, the co-radius is equal to the radius divided by norm z squared minus r squared. If you're bored, go do this exercise. Okay? So, once you have this, you do a little bit of algebra, very simple algebra from here, and you find that the bend is the reciprocal of the radius. The cobend is the reciprocal of the co-radius. So bend times cobend minus bend times center quantity squared is always equal to -1. This is just algebra from the first equation. So what does that suggest to you? It suggests quadratic forms. So what you should do is, to a given sphere, you should attach what we'll call the inversive coordinates, which are bend, cobend, and bend center. Then that will lie on the one-sheeted hyperboloid q equals -1. Because look at where q is this form, a half and minus the identity. Because look at what's happening here. It's a half b twiddle, and then minus the sum of the squares. Okay, so is that clear? That's where this is a universal quadratic form, regardless of what circle packing you're talking about, and it looks the same in all dimensions. Okay, so this point in Rn+2 actually lies on this one-sheeted hyperboloid q equals -1, or the real points of that. Is that clear? That's just algebra. So let's use this q as our inner product matrix. So this is sometimes called the Lorentzian inner product. Some people like to make a change of variables first. I like q just as it is. The signature of q is 1n+1. So that's why -1, maybe you're used to -1 being a two-sheeted hyperboloid. My signature is 1n+1. So this is a one-sheeted hyperboloid. And what's really going on, again, maybe this picture isn't the best one. I used to have chalk. There we go. So what's really going on is q equals 1 is a two-sheeted hyperboloid. And there's another sheet there. The point v, so what does this v have to do with the sphere, the initial sphere? It's very pretty. V has norm -1. These are the points that have q norm 1. V is the normal vector to a plane. So if you take the Lorentzian normal, the plane of all things orthogonal to V under this q inner product, the intersection of that will be a codimension 1 hyperbolic space. Okay, so the intersection of this plane with this one sheet of the two-sheeted hyperboloid is a one-dimension lower hyperbolic space. And the boundary of that, in your favorite compactification, unfortunately I can only draw in 3 dimensions, whereas it's supposed to be a 4-dimensional picture, right? Signature 3-1 for circles. So this is the circle. The boundary of this plane is the original circle. So what's really going on is, I guess the picture's up there, I'll draw it again here. You have your circle. That circle is the boundary of a hyperbolic plane. This is hyperbolic plane, which sits inside hyperbolic 3 space. And this is the boundary of the hyperbolic plane, the circle. Okay? So that's what this picture is explaining. Why these coordinates. Okay, there's some equation that told us what to do. No, they're very natural coordinates. They're coordinates describing this model of hyperbolic geometry. Okay, so and once you have this model, it's obvious what we're going to want to reflect through spheres. How do you reflect through a sphere? Well, once you have this model, it's just reflection through this plane. And how do you reflect through the plane? When you have the normal vector, it's this completely well-known fundamental formula for reflection. Does that make sense? So I'm just setting up a little bit of notation for what we're going to do. Okay, so let's look at Kobe-Andreev-Thurston from this point of view. So what is it saying? So another thing you should know is that this inner product measures the hyperbolic distance, or the Cauchy, the hyperbolic distance between these two planes. So if I have a sphere S1 and a sphere S2, and I take the hyperbolic planes for whom they are the boundary, then the hyperbolic distance between them, or the Cauchy of it, is exactly what this inner product is measuring. Okay? So what you can see from that is, well, we already know that if the sphere, if V1 is equal to V2, then we're taking norm of it squared, and the norms of all of these normal vectors are -1. These lie on q equals -1. So this VS has q of VS equal to -1, whereas the hyperbolic space is at q equals 1. Two spheres have inner product 1. That means the distance between them is 0. That means they're tangent. And the cosh being 0 means the distance is complex, which means cosh turns into a cosine, which means the two spheres intersect orthogonally. So spheres intersect orthogonally if and only if the inner product of their normal vectors is 0, or tangentially if 1. So what does that mean? So what is Kobian-Drev-Thurston? You give me the tangency data of your polyhedron with n vertices, and the dual polyhedron with m faces. Here's the equation you need to solve. You take v's, so the v's are the variables. The v's in the n vertices and the m faces will have self-inner product with q, which is what we call the supergramian. So it's the gram matrix not only of the vertices, but also the faces and what the intersection looks like. I'll give you an example in a second so you can see what's going on. So let's do the example of the square pyramid. That's kind of the smallest non-trivial, non-Apollonian example. So what's a square pyramid? You know what a square pyramid is. Well, you can read it off from this supergramian. So this part is the vertical dividing line, and this part is the horizontal dividing line. So the square pyramid has dual. It has 4 faces and 1 face that's touching all of them. Its dual is also a square pyramid. If you can see that. And let's look at this first line. So the index 1 vertex is, well, there's always -1s down the diagonal. That's because of that. But then this one is tangent to the second and the third and the fourth and the fifth. So that means that's the top vertex. He's tangent to 2 and 3 and 4 and 5. And he's orthogonal to 4 of the dual faces, because he crosses those faces. But I have no idea what the relationship is between the bottom face and the top vertex, so that's this dot. The dot is an unknown. It's another variable to solve for. Okay? So the tangency data, so the tangency data in this square tells you that you have a square pyramid. The tangency data here again tells you have a square pyramid. And this is the intersection of the faces, which vertices lie on which faces. So that's just purely combinatorial data that you stick into this partial gramian. And then you need to solve for these vertices and faces, and also these dots, which are also unknown, so that you get the equation, this thing times q, inner product with itself q, is this supergramian. So what is the super group? It's reflection through the vertices and the faces. And the Kobian-Drev-Thurston theorem is there is a unique solution. Up to orientation and Mobius transformations, there's a unique way to solve this equation that we've set up. So in the case of so here's the gramian. In the case of the square pyramid, remember we had these dots, these unknowns. When you solve it, some of the unknowns become 3's, and some of the unknowns become like 2 root 2's and root 2's and stuff. Okay? Does that make sense? Is it clear what we're doing? So this is the numerical step. You tell the computer, once you have this unknown data, you tell the computer, find me some numerical solution to this system of equations, incomplete system of equations, and whatever it spits, you then look to algebraize, and once it's algebraized, you check, do I really get this exact on the nose, the 1's and the -1's and the 0's, exactly where they're supposed to be. Okay? So what? I claim that this supergramian is everything. This is the whole game. Once you have whatever the supergramian happens to fill out to, these unknown values, they determine everything. They determine the entire arithmeticity property by a theorem of Winberg. So what's the theorem? So again, the supergroup is generated by reflections through the vertices and the faces, the polyhedron itself and the dual polyhedron together. That's the lattice. So it's a hyperbolic reflection group, finite volume hyperbolic reflection group. And its gramian is exactly this, what we called supergramian, G twiddle. So for the 4 pyramid, here it is again, just so we can stare at it. So here's Winberg's theorem. A hyperbolic reflection group, gamma twiddle, is arithmetic if and only if all cyclic products of, well, you're allowed to have half integers, so let's say twice the gramian, are integers. What does it mean to be a cyclic product? I start at this is what, the 1, 2, 3, 4, 5, 6, 7, 8 vertex. So I can go from 8 to 4 to 3 to 2, and